the last talk of the day, Jason Rute.
Thank you. Thank the organizers for inviting me and everyone here. So I'm going to be talking today about computable randomness. Now the question is, what makes a randomness notion robust? And luckily, Andre Nice kind of already had a discussion with this with Sasha Shen in front of us all. And it's there's lots of different ideas, and this is my list. I'm not saying it's your list; it's my list. But it's that these properties. It has many characterizations. So you can define it with Martin-Luft tests. You can define it with martingales, machines, etc. It comes up in computable analysis. I mean, that's really my interest, and I'm more interested in the types of randomness that come up in that sense. It generalizes to other probability spaces. It's preserved under alternate characterizations of the same space. So for example, Bayes invariance is kind of the big thing that people care about, but you can be much more general with this. And in some ways of being general with this is you can ask about morphisms or isomorphisms and whether those preserve the randomness notion that you care about. So the question is computable randomness robust? And by computable randomness, I don't mean, our field. That's algorithmic randomness. I mean a specific type of randomness that Schnorr came up with. And the question is this randomness notion robust? Well, first that we had a martingale test of it. I'll define it shortly, but we had a martingale test characterization of it. And then kind of all of a sudden a number of other tests came out using all these kind of standard machinery. So that's done. Now, one thing that was quite surprising actually is that this came up in computable analysis. This came up as a result of Brodka, Miller, and Nice, where they showed that it relates to the differentiability of a non-decreasing continuous function. Now, what about the rest of those list? Well, part of the result I'm going to talk about today is that, yes, it can be extended to other computable probability spaces. And it is preserved under alternate characterizations of the same space. Now, this was known already for Bayes invariance. That was Brodka, Miller, and Nice again. But in a more general sense, in that isomorphisms still preserve computable randomness.
What do you mean by Bayes?
I'll explain in a second what I mean. So, and then, but the surprising result is that it's not invariant under morphisms. And I'll explain all of this. This is kind of a high-level overview of the main idea. What? Oh, okay. Sorry, this is my first Mac. Oh, no.
It won't disappear, actually.
Oh, okay.
Enter full screen.
Sorry. We should get on with the talk.
You should just leave it.
Yeah. Sorry.
You have another CS1, right?
Wait, view, so full screen. Okay, sorry. Okay. Was this the next slide? Yeah, okay. So computable randomness, it's defined using martingale. So what is a martingale? We've already kind of seen it. It's a computable function on finite strings, which satisfies this property. But the idea is it's a betting strategy. It's if I give you coin flips, and I say, well, bet whether this is head or tails, and you wager some money. It can't be a negative amount. I mean, you can't go below the amount of money you have in your pocket, but you can wager that much, and it's just how much money you're going to win or lose. I mean, just how much capital you're going to have after the next bet comes up as 0 or 1. And then we say that a martingale succeeds if the amount of winnings you have is unbounded. Now, we say X is computably random if there's no martingale that succeeds on it. So in other words, you can't win any money betting on it. So now we'd like to first define computable randomness on other measure spaces. Or we'd like to define it on other measure spaces, but first let's define it on measures just on Cantor space. So let's take the Cantor space, but other measures on Cantor space. Well, a computable measure on Cantor space can be represented by a function, again from bits to non-negative real numbers, that satisfies this condition. So, and a probability measure is just one where the probability or the measure of the empty set is 1, and a fair coin measure is where the probability of a string of length n is. It's really just what you get from flipping coins. Now, measures and martingales, it's known that they're closely related. Now, if we wanted to find computable randomness on a measure on Cantor space, I found it most convenient to use this definition. Now, this of computable martingale. Now, this definition differs slightly from the definition you find in some papers, in that we still have the fairness condition that we had before. Now, of course, we have to weight the fairness condition, because if you're going to bet on a set that you know only has like a 5% chance of happening, given the information you know, you shouldn't win the same amount of money if you win on that set versus winning on a set that has a high probability of happening. I mean, you go to any racetrack and they know that fact. But there's also this other condition, which I'm going to call the impossibility condition, and that is that you can't, or that it doesn't really matter what you're gambling or what you're betting or what your winnings are going to be if you have a 0% chance of this event happening. Now, this is only going to come up if you have a measure that gives an open set or an open cylinder a measure of 0 probability of happening. So we call, in analysis, these are called, or the opposite of these are called strictly positive measures. And if a strictly positive measure, you don't need this impossibility condition. But with this, I find that it really is the right idea. And what it's saying is it's saying our martingale is not computable, but it's almost everywhere computable. And we can just define a string to be mu computably random if no such martingale, in this sense, succeeds on it. Now, a small question I have is, I don't actually know if this is strictly necessary. I mean, you can get away with allowing your martingale to be infinite. That would give you the same notion, although it's much messier to work with. But if you want your martingale to be finite, I don't know for sure that you don't need the impossibility condition. But yeah, what?
Well, what's about effectiveness? So you can detect that at this point you have measure 0 or not?
No, you can't detect.
Okay.
Just enumerable as
Yeah, exactly. I mean, once you know it doesn't have measure 0, you better give an answer at some point. But if it has measure 0, you can wait infinitely long to decide.
Yeah, but also you should see if sequence goes through the place when the measure is 0, it's not.
Oh, you're right. If it's in this null set, it shouldn't be random. You're right. Okay, so all these standard tests, except for the two starred ones I just haven't checked, but I'm sure they work. But all these standard tests work in this more general setting. And the proofs pretty much go through about the same, but again, you have to use this impossibility condition just to make, handle the fiddly cases. And so it's all listed up here. But again, this shows that computable randomness is kind of a robust notion. Using the graded Martin-Luft tests, the proof of those, I was able to extract also integral tests and Solvay tests. So kind of completing all the standard tests of Martin-Luft randomness.
The segment of third line is the same anyway, and the others were first. So
What?
the segment of third line is the same anyway, and the others were first. So it will
Well, okay, they're about the same. I mean, they're different definitions, but you could say a lot of these are the same if you translate between them. Yeah, exactly. Okay, so now what if we want to extend it to a computable metric space? Well, a computable metric space, if you've never seen one, I mean, most of this talk you can just think about Cantor space, but it's basically a complete metric space, a Poe space, where you have a countable dense set of points, and you can enumerate that countable dense set of points. And you know the distance between the countable set of points. And then you can, from that, get computable points, effectively open sets, effectively closed sets, all the standard sort of things that you have in Cantor space. And some standard examples are just the unit cube and the continuous functions. Now, the same way, you can also get a, or not the same way, but you can also define a probability measure, a computable probability measure on a computable metric space. And you can do that by, it's just a probability measure, a Borel probability measure. Every measure we're going to talk about is Borel. And where the integral operator is just computable. Now, it has to be computable on bounded computable functions because computable functions in general might not be even integrable, but bounded computable functions are, and this is enough to define it. It's equivalent to a number of other definitions, many given by Hoyrup and Rojas and other people. Okay, so how do you represent a computable probability space nicely? Like this definition we gave is useful in some sense, but it's not nice. It's not easy to work with weird randomness notions like computable randomness. Well, the idea is you treat it like it's Cantor space. Now, there's two ways to do this. You can either use isomorphisms to and from Cantor space, or you can decompose the space into cells. Now, these cells act like cylinder sets, and then you can kind of almost just automatically transfer your randomness notion. Now, of course, you have to make sure this works out right. So most of this talk, I'm going to use the isomorphism approach. And so a measurable map from one measure space to another measure space, we call it a morphism if it's measure preserving, if this property holds. Now, the idea behind a morphism is this first, so let's say the second space here, this y nu, that's like a three-sided coin, or even something more complicated like a like a computable Markov process with some sort of weird idea or weird definition. Now, if there's a morphism, well, that means that first space you could use to generate, like let's say you don't have a three-sided coin in your pocket, but you have a two-sided coin. Well, you could use that two-sided coin to mimic the three-sided coin, and you just think for a little bit, and it's obvious how to do that. Now, so that's the idea of morphism. Now, isomorphism basically means the spaces are the same, in a sense, and it just means you have a morphism that goes both ways. It's a standard category theoretic definition. Now, there's some basic facts of probability theory are that all spaces are isomorphic to the Borel measure on Cantor space. So again, in this, classically at least, you can think of everything as Cantor space. Also, all atomless spaces are isomorphic to the Faircoin measure on Cantor space. So you can think of any atomless measure as just, the Faircoin measure that we know and love.
Sorry.
Yeah.
Spaces are the Polish spaces.
Oh yes, that was it's all these computable metric spaces, which should really be called computable Polish spaces, because I don't want to deal with topological spaces in general. They're messy and So we wanted to find a computable morphism as just one that is a computable map. Now, well, what do I mean here by computable map? Well, this is where it gets, there's a lot of options. So the first option is we can use total computable maps, which in Cantor space would just be called truth table computable maps. And the idea is you take in a Cauchy code as input, and it always returns a Cauchy code as output. And if you map to the set 0, 1, well, each of the, if you map back, all the sets that return, or all the points that return 1 or 0, well, that has to be a decidable set, like an effectively Clopin set. Now, this isn't a very nice notion because we can't even do like the reals to the binary expansion, because it's not going to behave well on rationals. But the rationals are measure 0 sets. So you're like, well, okay, what if we leave out a measure 0 set? So this is almost everywhere computable maps. Takes in a fast Cauchy code, returns a fast Cauchy code with probability 1. And again, equivalent inputs equal equivalent outputs, but again with probability 1. Now this turns out to be very closely related to Kurt's randomness, which I'm not going to find, but it's just, it's a weaker notion of randomness. And if a function,
Sorry, but probability is not on codes, but what does it mean?
Wait,
So
what?
On sequences, on points.
Yeah.
So when you say the equivalent input codes.
Oh, for a given point. So if a point has two equivalent Cauchy codes, almost everywhere they must, almost surely it must return.
So the set of points for which this is violated is of measure 0.
Where it's what?
Violated.
Yeah, it's measure 0. It's really what you would think of an almost every computable map is. It's just a map that's computable on almost every point. And if we map the sets 0, 1 back, those are each what we call almost everywhere decidable. You can decide it almost surely. Now, you could even take this farther. You could say, well, I don't really care if I'm wrong for a small epsilon as long as I get to define what epsilon is. As long as I get to say what epsilon is. So you could take in an input and return an output, well, and you'll get an output with probability 1 minus epsilon. But you get to pick the epsilon, so that's the key point. And this then is unique and well-defined on Schnorr randoms. Again, I'm not going to define it. It's a stronger notion than computable, or weaker notion than computable randomness. And But the nice thing about these is, whereas the other maps are only almost everywhere computable, these maps are measurable. And in the strong sense in that, relative to an oracle, they are the measurable maps. You can also think of this in another sense where I'm slightly changing this last definition, where we don't care now if the points have inputs or outputs, but they're just defined in a more general sense. There's a nice metric to define these, but you can define effectively measurable maps. And these are maps that take the inverse image of an effectively measurable set, which can again be defined in a metric, is effectively measurable. I'm going to mostly be using in this talk the almost everywhere computable maps, but I wanted to mention those other ones because I think in general they're the better notion. So, yeah, with the other ones, these results basically still hold, and even with the effectively measurable morphisms, you can still talk about randomness, but now randomness becomes generic filters like in solid forcing, because you can't talk about points anymore, because they're not maps that actually map points to anything. Okay, so Hoyerup and Rojas showed that there is a computable isomorphism between a space and between any space and Cantor space, with some measure on Cantor space. If you know some probability, that measure is just the distribution of the map that you're defining. Now, we can define then computable randomness to just say, well, pick one of these isomorphisms, and X is computably random if, when you map it to Cantor space, it's computably random. Now, this definition would work fine. Now, some people might complain that it's ad hoc or whatever, but it would work fine as long as you didn't care which morphism you picked, or which isomorphism you picked. And that's one of the results, is that it doesn't depend on the actual isomorphism. And you can also compare this to another theorem, which a lot of people know, is that if you take an almost everywhere computable morphism, and X is something like Martin-Luff random, and you map it forward, you're going to get a Martin-Luff random again. And this holds for Schnorr randomness, it holds for Kurtz randomness, it holds for all the different randomness, I think all the different randomness notions that Andre mentioned. But here's the thing, it doesn't hold for computable randomness. Computable randomness doesn't hold if you just map it forward, or it doesn't stay preserved if you map it forward with one of these morphisms. I mean, and it actually, it could be even computable. Like if you're talking about Cantor space, it could be TT. I think it could be a TT mapping. But what you can preserve is if it's an isomorphism. You can preserve computable randomness. So before I kind of get more into the details of that, let me just mention some examples now that we have a definition. Well, randomness on the fair coin measure. I mean, computable randomness will stay the same just because you can use the identity isomorphism, and it's invariant under our isomorphisms. Now, randomness on the Lebesgue measure. You can use this, just the basic isomorphism that everyone uses anyway, that computable randomness, something's computably random if and only if its binary expansion is. Now, this is where base invariance comes in. Now, base invariance is, what if we define computable randomness on like 3 to the omega, or 4 to the omega, or 5 to the omega?
Surely this was known long ago.
Computable randomness? Maybe.
Surely it was proved by Jack Lutz like a decade ago.
Okay, that might be. Wait, what was the
base invariance?
Okay, yeah. I'm not claiming that I proved base invariance, and they give a proof. So if you can't come up with one on your own and you can't find this paper then, but I could be. It very well might have been proved before. Do you know, Andre?
We discussed and it was hard to find a printed reference actually, but there have been claims that it was done in some way. Is Jack around?
Yeah, he's not around. We should ask him.
Yeah, but we had a similar discussion already at the
Yeah, the problem is the printed reference.
Okay. Well, I don't have much time left, so I'm gonna keep talking. Okay, so Lebesgue measure. Again, you can use kind of this standard isomorphism where you just take the binary representations of all the points, join them together, and see if that's computably random. Now, what about something more interesting, like Brownian motion? Well, there's a nice isomorphism between the fair coin measure and Brownian motion. I believe that Willem Fouché has shown that it's a computable isomorphism. Have you, right?
it's computable towards the codes of the continuous function.
Okay.
The Levy isomorphism. It's not continuous as it stands.
It's not continuous? Okay. Okay, so maybe I do need to check
I'll
this.
discuss it.
Yeah, okay, yeah, sorry. But if that's true, anything that you have a nice isomorphism with, you get computable randomness.
Sorry, there is a continuous isomorphism, but the Levy isomorphism is not continuous.
Oh, okay, there's another one, and it's computable. Okay, so use that one. Yeah, sorry. Okay, so now how do we think of morphisms? Well, we normally think of them as forward maps. You map a point to a point. But they're better to be thought of as backwards maps. You map a set, a Brell measurable set, to its inverse. And recall that this was going to have the same measure. So if you think about something like preservation of randomness, it's the same sort of thing. You could think of preservation of randomness, for example, on Martin-Liff randomness, as I take a Martin-Liff random and I get a Martin-Liff random. But what it's really saying is in the domain, in the range, if I take a Martin-Liff random test, I can map that back to a Martin-Liff random test. Now, why is that true? Well, it's true because morphisms preserve the measure, and there's almost everywhere decidable stuff. It basically preserves effectively openness. It doesn't exactly, but it's close enough. And it's true for other complexity classes too. That's why all these randomness notions defined just by measure, where the tests are just sets of some complexity that are combined in some way, then with some measure bound on the measure, then they all preserve this. They all have this preservation of randomness. Now we'll see in a second what's going wrong with computable randomness. Now, if you're given an almost everywhere computable morphism, you can take the sets that just say, so y is in the domain, so the nth bit of y is 1. If you knew whether y was in or out of all those sets, you would be able to find y. You just, what's the 20th bit? Well, is it in the set that says the 20th bit is 1? Well, you map these sets back, and you're going to get something that says the nth bit of t of x is 1. Well, these sets are almost decidable, and so there's some family of almost decidable sets that determines the morphism t. And more than that, if you just take any family of almost everywhere decidable sets, you can get some morphism from that. It's just a morphism that says, these are maps to Cantor space. It gets some morphism that says the fifth bit of the answer is whether you're in your fifth almost everywhere decidable set here. So in that sense, every morphism defines a family of sets, and every family of sets defines a morphism. So now we can talk about mapping martingales back. Because remember, the idea of proving preservation of randomness is you want to take a test and you want to map it back. So now I'm taking, my test is a martingale, as I defined it, and I want to map it back. Well, what do I get when I map this martingale back? Well, what I get is I still get a betting strategy. I still get a fair game betting strategy, and I basically get the kind of strategy that the last year was talking about. The idea is that you're betting whether the nth bit of the image is 1 or 0. But what I already said is that any morphism can basically just be described a bunch of sets that basically determine whether the nth bit is 0 or 1, or the nth set determines whether the nth bit is 0 or 1. So really you're betting that it's in some set or some property. So what I'm doing is I'm just taking a bunch of properties, and almost everywhere decidable properties, and I'm betting whether it's in that property or not. Now, of course, I need to get fair odds based on the current knowledge I have and the size of the set relative to that current knowledge. But this is exactly what's going on here. And this is basically martingale processes of Hitchcock and Lutz. The only difference really is that theirs are decidable sets, where here it's can be extended slightly to almost every decidable sets. But it also includes non-monotonic martingales, so like the type that define Kolmogorov-Loveland randomness. So, for example, in a non-atomic martingale, maybe A0 is that the fifth bit is 1, and then A1, the next thing you're betting on, well, it can be two. It can be the union of two sets. So one is like if my first bit was 1, then it's this stuff. Well, that has to be, within the set that says my first bit's 1, and then or maybe the first bit I bet on was 0. Then it says that maybe I'll bet on the 10th bit. So with a little work, I mean, this is not completely obvious, but it follows that preservation of randomness doesn't hold for computable randomness. And actually, I forgot to. Bienvenu and Porter also had a similar observation. So, but if we have an isomorphism, then something kind of special happens. These sets that define our isomorphism, because remember, like I said, a morphism is just defined by a bunch of sets. So these sets that define our morphism, well, they basically become a topological basis for the space. And this was actually noticed already by Horup and Rojas, that this idea of this interchange between getting a topological basis. Basically, I mean, the issue is they're almost decidable sets, so they're not really open sets, but they're close enough to open sets that it's just an almost everywhere thing. It's, for every open set you can get a union which almost everywhere equals that open set. And so this correspondence was already known by them. And the converse also holds. If you have this family that's topological basis, then it's an isomorphism. So the martingales, when you map them back, well, now what you're going to get is you're going to actually be able, when you bet on a point, you're not going to be betting necessarily on cylinder sets like you normally do, but you will be able to, at the end of your betting, after infinitely many bets, you will be able to know exactly what that point is. This is where kind of this topological basis idea comes in. And this is enough to then show that it actually is the same thing okay, so like on 2 to the omega, if x was 2 to the omega, you could show it's the same thing as computable randomness. Or in general, you can show that it's invariant under the choice of t, which is, again, my main result here, is that you can show that this choice of t doesn't matter when defining computable randomness. And what this gives you is a martingale test for computable randomness on any space, where you just pick these sets that have this certain property and bet on them. But also the other tests can be extended. Like so all that first list of tests, except for the 2 starred ones I just haven't checked, they can all be extended. I mean, quite naturally to other spaces. And it follows then that computable transformation or computable isomorphisms preserve computable randomness. I mean, again, it takes just a little bit of work to see why that's true, but it follows. So that's true. So, okay, so this is this slide will get lost on odd people just because I have a short amount of time, so I'm sorry about that. But the general idea is this can be applied to even something interesting like computable analysis. Okay, sorry, I didn't mean to imply that computable randomness in itself is not interesting, but I kind of came at this thinking about how can I apply this to computable analysis. Well, there's a more general notion of martingale that's used in computer science, and the martingale processes of Hitchcock and Lutz were designed to basically kind of get one step closer to that. And you can even get a little closer to that. So what a martingale is you have a bunch of functions. These functions are the amount of money you have at time n. So we think about it differently. You think of the function as a function on your point, but then you have 1 for each time. And the idea is the amount of money you're going to have at time n plus 1, the best guess you have of that based on your current sequence of betting and whether you won or lost is the amount of money you had at time n. So an interesting thing or a thing that a lot of probabilists are interested in is not winning money on these martingales, although that's interesting too, is whether they just converge. And what you can show, or what I can show, is that if you have an almost everywhere computable martingale, so a uniform sequence of almost everywhere computable functions that satisfies this martingale property, and what's known as the L1 bound of that martingale is computable. So it's the supremum of the L1 norm of each of these functions. Then and there's this weird condition that the limit converges to in an effective way to some sigma algebra, which is, I mean, really vague on, but the idea is the sigma, each of these times you bet, you gain information, and that's a sigma algebra. And so at the end of your betting, you have some kind of sigma algebra. And I'm sorry, I know a lot of you probably are lost here, and that's fine. This is the second to last slide. But if that sigma algebra, if you can compute the expectation relative to that sigma algebra, then you're going to converge on computable randoms. But this idea isn't going to work for the ergodic theorem, and I'm not even going to mention why, because, I mean, if you're interested in ergodic theory, you can ask me afterwards. Okay, so to summarize, if we generalize randomness notions like computable randomness to other spaces, we can actually get a better understanding of the space on Cantor space. Like, we can think about like this idea of betting on sets that aren't cylinders and stuff like that. There's a duality between morphisms and representations of a sub-sigma algebra of space. I mean, this is well known actually in analysis, or in ergodic theory, it's called factors. There's also a duality between isomorphisms and the representations of a probability space. So if you want to represent a space as Cantor space, you can do that using isomorphisms. And they kind of help to classify what are the good randomness notions, the bad randomness notions, or at least the robust ones. So for example, I can show that anything between Martin-Wolf randomness and computable randomness is not invariant under morphisms. If Kolmogorov-Levin randomness is invariant under isomorphisms, and what I mean here is under isomorphisms where you also consider other measures on Cantor space but take the obvious extension of Kolmogorov-Levin randomness, then it is equal to Martin-Wolf randomness. And just a question would be, I haven't really thought about this at all, but is something like partial computable randomness, is that invariant under isomorphisms? It's not invariant under morphisms, but maybe it's invariant under isomorphisms, which at least shows it's somewhat of a robust notion, but maybe it's not. Maybe it's a horrible notion. I don't know. Okay, so my talks will be available on my website, and if, you can find that just by Googling my name. Thank you.
Any questions?
Yes, Quinn. Oh, sorry, you're supposed to.
In your Martingale convergence one, I guess it was the second to last slide. Do you have any conjecture about the other direction? About
whether it's
maybe whether it characterizes or whether.
Oh yeah, I mean yeah. The other direction is kind of obvious because you just take a martingale in the normal sense, and it's of this type. Because if your martingale is positive, sorry, you can't see 1 point. If your martingale is positive, then this computability condition of the supremum of the L1 norm is just trivial. It's the L1 norm of, well, it's your starting amount of money. And as far as converging effectively to the sigma algebra, it's just going to converge effectively to the Borel sigma algebra. So it's an if and only if in that sense.
Partial computable randomness on Cantor space is not preserved under computable permutations.
Okay. Wait. Oh, computable permutations. But are they isomorphisms, or are they just?
What not preserved?
Partial. Just please go back to the last slide. Here.
Yeah.
Partial computable randomness not preserved under exchanging the bits in a computable way.
Okay, so that you still bet on every bit? No, that or.
Yeah.
Okay. So well then it's not. Okay. Okay. Yeah. Sure.
So there is a very, very basic question. So you explained that there is a good notion of computable randomness for more or less any computable metric space.
Mm-hmm.
But can you say, imagine that you want to define computable randomness for a point in a plane or in a unit square?
Well, those are computable metric spaces.
Yeah.
Okay.
We want to give a definition which doesn't involve any base.
Okay.
So what is the direct definition?
Okay.
What kind of game maybe you
So, I mean, computable square, the game, I mean, would be the obvious one. It's just you break up the space like this and you bet on it. And then you break up like that.
But so you can just divide into any more. You don't need to use base 2. So I want it to be base invariant.
Yeah, it's definitely base invariant under your. I mean, you have to make sure that you have something that's going to generate the Borel sigma algebra. You can't just leave this touched and every time you go you just leave it as a big square. Then it's not going to be good enough.
So, but for example, if you just divide in any number of I don't know, polygons, it's okay.
If the polygons generate the Bell-Sigma algebra, yes.
Okay, I think that's enough questions for today.